Okay, let's get started. Yeah, so the title of our paper was Fast and Simplex, Two Simplicial Attention in Triton. Although a few people in Twitter proposed an even better title, which was Too Fast and Too Simplicial. So maybe we should have gone with that. So this is a collaboration with a bunch of awesome folks at Meta, Tim Chow at Meta, Sai Surya, who was interning at Meta, he's at UT Austin, Sijia Chen, Jie Chao, Xiaodong, Manzil, and Rohan. Rohan also did this work while he was at Meta. Right. So yeah, so what's sort of the high level abstract or sort of the motivation for this work, right? So as we all know, that the current scaling paradigm, which is the transformers, right? So the way we sort of approach the science of scaling is through this lens of scaling laws, right? So where we sort of posit that the training loss is scaling as a power law in terms of the number of parameters of the model and the number of tokens that we train on. And so we sort of currently have this paradigm of compute optimality, which means essentially how quickly can we reach a certain training loss with, say, the minimum amount of compute. So various algorithmic tricks, data tricks, optimization tricks, all sort of chase after this compute efficiency wins, right? However, as we sort of, if we think about these scaling laws from first principles, what we sort of realize is that they have an implicit assumption baked into them, and that implicit assumption is that there is an infinite supply of tokens. There is an implicit supply of high quality data. So as we sort of as these large labs, AI labs, essentially start sort of start training these giant models on pretty much most of the internet now, right? So we're sort of starting to reach the point where we are seeing that this assumption is no longer true, right? So the assumption for compute efficiency, or sort of playing the compute efficiency game, is that we are compute bound, right? And that we have an infinite supply of tokens. So what are all the algorithmic and computational tricks we can sort of come up with to lower the compute and get to the same loss, right? So that assumption is becoming less valid, right? So what we're sort of reaching the point is compute is relatively cheaper now, right? And it turns out that high quality data is the bottleneck, right? So all of these AI labs are building investing in huge data centers. But on the other hand, let's say high quality books that have high quality signal, those are not being written as fast as we are investing in our data centers, right? So that's sort of the bottleneck. So really what we should think about is how can we spend compute more cleverly, right? So that's the kind of question. So given that we have a finite number of tokens, how can we sort of spend compute more cleverly to extract more signal from the finite set of data? That's sort of the motivation for this work. And in this work, we essentially go back to the literature, and we sort of figure out that there are some papers that had proposed some generalizations of dot product attention. Essentially, in particular, this old paper from 2019 called Two Simplicial Attention. And what they essentially propose is they propose doing dot product attention. They propose a generalization of dot product attention to trilinear forms. And back in 2019, I guess it wasn't as it was sort of ahead of its time because we did not have this problem back in 2019. But I guess so. This is now a good time to revisit that problem and revisit that research. And in particular, we show how to make this trilinear attention practical by essentially adapting it with more efficient forms of attention, and we open source a Triton kernel implementation of it. And we also show with experiments that this form of attention, this trilinear attention, achieves better token efficiency than standard transformers. So if you fix the token budget, then a similar sized model of two simplicial transformer outperforms the dot product attention counterparts, especially on coding, reasoning, and math heavy tasks. And more specifically, the way we quantify these gains is by showing that if we sort of look at the scaling law plot, we sort of quantify these gains by showing that two simplicial attention essentially changes the exponent in the scaling laws for these knowledge and reasoning heavy tasks compared to dot product attention. So that's sort of the overview of our paper at a high level. And right, so I guess at the heart of all this is what we sort of call scaling laws, right? So large language models are not new. They came, everything started with Vaswani et al. In 2017, and since then people have been sort of figuring out, have been scaling transformers, starting with GPT-2, GPT-3, GPT-4, Gemini, Llama, and so on. And the remarkable progress in scaling these models has essentially been unlocked by neural scaling laws, right? So if we look at scaling laws, the main contribution was the paper by Jared Kaplan, and Hoffman et al. And chinchilla scaling in particular shows that the chinchilla model with 70 billion parameters outperforms a much larger gopher by training on 4 times more data, right? So it wasn't only sufficient to scale model parameters. One also needs to scale the data to lower the loss, right? So I won't go through this again since I sort of talked about this already. I will also not go through this. The only other thing I want to mention is, right, so there has been some prior work besides Clift et al. In sort of thinking about higher order attention. Related work is Bergen et al., which proposed edge transformers. AlphaFold also uses an attention mechanism, which is similar to the edge transformer, which is induced by the 2D geometry of proteins. Higher order interactions were also explored in Wang in the context of recommender systems. And in particular, I also want to call out this work by Sanford et al., which is essentially identical to Clift et al. And they sort of show theoretical results. They essentially show a hard problem for transformers. And the hard problem is sums modulo 3 sums modulo a number. So they call this class of problems match 3, and they show that dot product attention or transformers have a hard time solving this problem. And by a hard time, we can quantify this essentially as they require exponentially many layers in the sequence length to solve this task. Their original motivation was essentially showing a separation between transformers and LSTMs, or recurrent models. And they showed the separation for match 2. So match 2 is sums modulo a number. This is equivalent to the ZAR problem, right? So it's well known that LSTMs and RNNs have a hard time solving ZAR, whereas transformers can do it in a fewer number of layers. And there has been some other interesting work on proposing some scalable approximations to this sort of higher order attention problem. The other work is related work is looping transformers, and looping sort of has a similar idea where you want to keep the model parameters fixed, and you loop the model, uh, let's say k number of times, right? So the motivation behind looping is also that you want to compute a more expressive function per parameter. And there has been some recent work showing that they perform better at logical reasoning tasks. However, looping has some problems. One problem is looping larger models is sort of an open question in terms of their trainability, since as you loop more, you start suffering more from vanishing or exploding gradients. The other problem is, can we transformers, so looping can only shift the error, right? So in order to change the exponent of scaling laws for transformer, you need to do something that is not simulatable by a constant iteration of transformers, right? So in order to shift the exponent with looping, as the model parameters increase, you need to start looping more and more. So asymptotics of looping, to change the error, you need to, so you can't loop a fixed number of times to change the error, to change the exponent, in order to not be simulatable by a fixed number layers of transformer. Okay, right. So yeah, so more specifically, the scaling laws essentially look of this form, where we essentially have an irreducible error. This is essentially the entropy of text or math or code or whatever test set that we want to measure. And we posit that the loss essentially decreases as a power law in the number of parameters and the number of tokens, right? And so what we notice from this is we can only approach the reducible entropy of text if we have uh, infinite number of data, right? So d has to go to infinity in order for this term to vanish, right? So in order so I won't go into chinchilla scaling. So this is essentially, through several experiments, the authors of Chinchilla found that alpha and beta were roughly similar, right? For transformer, alpha and beta are roughly similar. So in order to have compute optimal transformers, as you increase model parameters, you need to scale the number of tokens similarly at a similar pace, right? So when could this change? This could only change if, for another class of model architectures, we have an alpha, right, that is significantly different, or at least for some tasks is different from beta, right? So if two simplicial attention has a higher alpha than a beta, then for two simplicial attention, as we scale the number of parameters, we do not need to double the tokens for every doubling of parameters. We can grow the tokens at a slower pace compared to transform, right? So this is where the advantage of a higher alpha comes in, right? So let's look at what is two simplicial attention. So if we recall dot product attention, we have essentially given a sequence X. So we have n cross D. So n is the sequence length, D is the hidden dimension. So we essentially have these learnable projection matrices in D by D, right? So they give us the queries, the keys, and the values. And this is what is used to construct the attention logits. It's essentially QK transpose, and there's a square root D scaling factor. And we can essentially look at the I comma jth term of this matrix. This will be the dot product Qi comma Kj, right? Proportional to the dot product of Qi Kj. And then the attention operation essentially transforms these logits into probability weights, right? So we essentially do a softmax over the rows. So we essentially exponentiate the entries of the attention logits, and we sum over the j's, right? So for every I, we assign every token I, assigns a probability score to every token j in its context, right? And this essentially gives dot product attention. And here we ignore masking, causal masking, and so on, right? So the geometry of dot product attention essentially is that of a simplex, one simplex, where if we look at the softmax of dot product attention, it's going to be a probability simplex between I and j, right? So every I depends on one particular j. And in two-simplicial attention, we sort of extend this to the two-simplex, where every I now has an interaction on this triangle j comma k, right? And the way this works out is, in addition to wk and wv, we introduce wk prime and wv prime to produce these two pairs, wk prime and v prime, right? And so now we can start thinking of how can we give it an attention score or an attention logit. Well, we can start with simple trilinear products first, right? So we can give it a score A, I, J, K, which is Qi, Kj, K prime, K. So it's a three-way product between these vectors. And that three-way product is essentially sum over their hidden dimensions, right? So if L goes from 1 to D, QIL, KJL, K prime, KL. So if K prime were 1, right, so this would essentially be dot product attention, right? So this is a generalization of dot product attention when if K prime is the constant one vector, then this just recovers dot product attention, right? And the attention tensor is then, so now for a particular row, we now normalize over not just the j, not just the column, but we normalize over j and k, right? So we normalize over the last two dimensions of this attention tensor, right? And then, and similarly, the final output of the attention operation is now going to be the sum over j comma k of the softmaxed entries, and then you have vj Hadamard vk, right? So vj's are the value vectors obtained from, so vj is the regular value, and this is the third tensor value obtained from v prime, wv prime, right? So this is sort of the map behind it, right? And so if you were to sort of do it naively, right, how would you do it? It's you would essentially have the simple function qkv, and then you would have k prime v prime, and then you could write it as an einsum. So if batch, you have the batch dims, you have the time dim, you have the num heads dim, and you have the hidden dim, right? So you have btnh, bsnh, brnh, right? So these are your inputs, q, k, k prime, and then you essentially einsum that to a bntsr tensor. And then you compute your attention with softmax, with causal mask, and you essentially softmax over these last two dimensions. And your output again is going to be bntsr, bsnh, brnh, and you essentially you einsum it with the two value vectors, right? And you get the out. So if k prime and v prime were all ones, it's easy to verify that this would just be dot product attention, right? So this is great, and this actually already works, but there's some interesting, so trilinear forms are a more expressive class of functions than bilinear forms, and one thing to think about is positional information, right? So positional information in state-of-the-art transformers is usually the rope encoding, where rope essentially applies a position-dependent rotation to the queries and the keys, right? So you apply a rotation proportional to I, to the query's qi, and you apply a rotation proportional to j for every key kj, so that your dot product qi kj is now going to be a function of the distance I minus j. Right. So if you apply, so if you do the simple trilinear function, right? So we apply a rotation proportional to I to the queries, we apply a rotation proportional to j to the keys, For the third tensor, we do not apply a rope because it does not make sense for the simple trilinear product. And why does it not make sense for the simple trilinear product? This is because dot product attention is invariant to rotation. So if you apply a rotation to dot product, the same rotation R to a dot product QI you apply the same rotation to QI and same rotation R to QI and KJ, the dot product is invariant, right? So in particular, this means that the dot product for the same entry I is not shifted. So the dot product when I equals J, right? When I equals J is unaffected by this rope rotation. However, what we find is the simple trilinear product, Qi, which is the sum of the three wave vectors, this is now no longer rotation invariant, right? So if you apply the same rotation R to each of these vectors, right? One can verify that this simple trilinear product is no longer going to be the same. So in particular, you cannot apply a rotation, the rope rotation to the third tensor, right? Because for the same position, you are going to get an offset, and this will not work out, right? So how do we sort of think of so the thing is, we can start thinking about we're no longer tied to this simple trilinear function, right? We can start thinking about more expressive functions that preserve rotation invariance. And in particular, there are several such functions, but one particular function that we found is invariant to rotation is determinants. And determinant in the context of dot product is a slight shift from scalar product, right? So if we have A1, B1, A2, B2, so the scalar product of the vector A1, B1, and A2, B2 would be A1 times A2 plus B1 times B2, right? Whereas the determinant is A1, B2 minus A2, B1. So this is also a bilinear function, as can be verified similar to a dot product. And to remember what a bilinear function is, it's essentially if I apply a scalar linear transformation on any of these vectors, the final function should be a similar scalar multiple of that function, right? So if I multiply A by lambda or B by lambda, the final function output should also be lambda times this value. So that's the definition of a bilinear function, right? So this is a bilinear function that is rotation invariant, similar to dot product, but it has the nice property that when we look at triples of functions, three-way functions, the determinant is rotation invariant compared to dot or the simple trilinear function. So if we look at the determinant of three vectors, A1, B1, C1, so this is a three-dimensional vector. This is a three-dimensional vector, and this is a three-dimensional vector. And we're looking at the determinants of these three vectors. What we find is the determinant is rotation invariant, right? Because the determinant essentially captures the volume of the parallelepiped spanned by these vectors. So if I apply a rotation to one of these vectors, to each of these vectors, if I rotate each of these vectors by the same amount, by the same angle, the volume of the parallelepiped spanned by these vectors is unchanged, right? So it's essentially this volume, signed volume, right? So this is unchanged by rotations, and this can be implemented essentially by two einsums. So instead of the single einsum of the simple trilinear product, this would be two einsums and a roll. So you would take A1, A2, A3, you would roll this, the two vectors, you would roll this by one, you would roll this by two, Here you would roll this by 2, you would roll this by 1, and you would compute the einsums of this. And this would essentially be, yeah, 2 rolls and 2 einsums. And you could define the logits essentially as, so you would divide the hidden dimension into chunks of size 3, and you would compute the determinants of these 3 cross 3, 3 by 3 matrices. And you can do this efficiently by 2 rolls and 2 einsums. And what we show is that this is now rotation invariant. So you can now add rope encoding to the third tensor, right? And you will start seeing some benefits over not adding rope and the simple einsum. And what we show is theoretically also that this has similar expressivity as the simple trilinear function. So what we show is that, similar to the match 3 result, that if we swap out the trilinear attention with this determinant function, we can show that that this can also compute match 3 efficiently. So this has similar expressivity as a simple trilinear function. All right, so you can use either of these trilinear functions, or you could even come up with other trilinear functions that are rotation invariant. But the crux of the matter is, no matter what trilinear function that you use, you are going to bump into a cubic complexity, right? So even if you want to compute determinants, or if you want to compute the simple trilinear function over the whole sequence, if the sequence length is n, what ends up happening is this is no longer feasible. This becomes n cubed, right? So the way to solve this problem, and the way to solve this expressivity problem, is to parameterize it as n times w1 times w2. And here w1 and w2 essentially refer to the size of a sliding window over these 2 dimensions, right? So if you ignore w2, so this is going to be sliding window attention, right? N times w1 is linear attention, and this linear attention is what we call local attention or sliding window attention. And this is actually a very important and useful baseline for attention, right? So in 2020, 2021 period, many linear forms of attention were proposed, but the one that has stood the test of time and is used everywhere in practice is local attention or sliding window attention. And the reason that local attention is used is because it has the benefit of expanding receptive field with stacking, right? So if we have 2 local attention layers, right? So if we have the first layer, which has a sliding window of size W1, and we have a second layer, which also has local attention with sliding window size W1, then the second layer actually has a effective receptive field of 2 times W1. So it doubles with every addition of the local attention layer, right? This is due to the the strided interaction of the local attention layers. So in particular, because of this exponential growth, one can also show theoretically that sliding window attention with parameterized with this cubic whatever higher order attention can also solve match 3, or can also solve that threesome problem with a polynomial number of layers. Why? Because it can essentially compute attention over the whole sequence by a polynomial number of layers, because of this growing with receptive field, because of its doubling with receptive field, right? So essentially, this is the right parameterization in order to make this efficient, right? And this can actually be visualized in this cubic tensor, right? So we have the queries here. So this is one axis. We have the keys k prime, and we have the k prime on the third axis. So this is sliding window 3D attention on with a causal mask, right? So if you look at the first few queries, it's attending to sort of this local neighborhood, and this local neighborhood sort of grows and it reaches the maximum, uh, which is W1 and W2, and it's essentially sort of carves out this. If you were to do the full attention, you would get sort of this whole cube, whereas sliding window attention essentially carves out this tunnel through this whole cube. And yeah, so this sort of goes, yeah, this sort of carves out this expanding receptive field over this cubic tunnel. And I won't go into too much details of the hardware optimization, which I will leave to the future, or to people who are more familiar with the hardware part. I'm not an expert on the 3D flash attention and the CUDA cores. So another thing to note is that as we sort of look at the growth in terms of latencies, as we increase the two simplicial attention, as we increase the sequence length, the sliding window to simplicial attention grows linearly, whereas standard attention grows quadratically. So there's a crossing over point around 48K, right? So if we imagine that we are serving our language models, right, which have global layers, global attention layers. So if we have global attention layers, if we are serving a language model with global attention layers which are larger than 48K, right? So let's say we are serving a context length of 1 million or 2 million or 128K or 256K. So then the bottleneck in your attention layers is always going to be the global attention, right? So that global attention layer will start dominating. So sliding window to simplicial attention will win out if you have global attention layers in your setting which are larger than 48K. So then what you can do is you can pipeline, right? Let's say if you're using pipeline parallelism where you have like local attention layers and you have some global attention layers which are serving more than 48K. So then you will start getting bottlenecked on the global attention layers, right? So then you should always include two simplicial sliding window on the local layers, because yeah, otherwise your global attention layers larger than 48K will start becoming a bottleneck in your pipeline parallelism. So I won't look into the backward pass. Right, so let's see how we can sort of think about the results, right? So the way I set up the results was I started doing experiments on 1B, 2B, and 3.5B parameter models. So the two simplicial attention has slightly more parameters because of the WK prime and WV prime. So in my uh, uh, coefficient calculation, I use the exact number of parameters, right? So what are we trying to do, right? So we have the loss, we fix the number of training tokens, right? We fix the total training budget, so then we can sort of fold this into the irreducible loss. So this becomes E prime. And now we have a power law essentially only in the number of model parameters, right? And this can be approximated if you take the log as a line, right, where you have a slope and an intercept. So if you ignore the intercept term, what you really care about is the slope term. And you have log loss and you have log number of parameters. So anytime you can change the slope, you can change the exponent in the power law scale. So what I did was so the minimum number of points you need to estimate a linear plot is 3, right? So I trained 3 models, 1B parameter, 2B, and 3.5B. And I fit the log loss, and I fit the exact number of log parameters. So two simplicial attention has slightly more parameters because of the extra WK prime and WV prime. And again, the experimental setting was 1 every 4 layer is 2 simplicial attention, right? So it's every 4th layer is 2 simplicial attention to distribute, as I mentioned, to distribute the load with full attention, right? And then what I mentioned, what I measured is what I care about is the alpha, right? So what we find is on tasks on GSM8K and MMLU Pro, which are more challenging and less saturated than MMLU and MBPP, we find that 2 simplicial attention is able to drive down the loss further in terms of having a larger alpha. And you see some gains on MMLU and MBPP, but not as much. So the extra amount of compute that you spent on 2 simplicial attention, it was able to drive down the loss on GSM8K and MMLU Pro more compared to, let's say, MMLU and MBPP. And on other natural language tasks, such as summarization and question answering, there was no improvement. So it was sort of neutral. So adding more compute onto simplicial attention only makes a difference for logical reasoning, coding, and math tasks. So that's sort of the summary. Right. So to recap, what we showed was, right, to recap, what's the motivation? The motivation is we are no longer compute bound, we are data bound, right? So what that means is if we can find architectures which have a larger alpha, then if we do the chinchilla compute optimal scaling of this architecture, if it has a larger alpha compared to beta, right? So then we can increase the model parameters at a faster rate than increasing the number of tokens. And this makes sense when we are token constrained rather than compute constrained, because we are spending more compute or more flops. So we're increasing the flops on attention by doing this sort of 2 simplicial higher order attention. And what we're showing is we can sort of drive down the loss on math and reasoning tasks. And what we show is that this changes the alpha, right? If we plot the loss per task, if you break down the scaling loss per task or per category, right? If we break down the scaling law for math tasks and reasoning tasks and coding tasks, what we find is this higher order attention can change the exponent for scaling um, for these kind of tasks. And so, yeah, so to conclude, we are no longer compute constrained. Rather, we have more compute and we have less high quality data. We want to scale architectures that compute more expressive functions per parameter so that we can make better use of this finite amount of data. And this essentially is one promising direction that, that we as a community should explore more. And yeah, so I would like to thank all my other awesome collaborators at Meta and beyond, Chuan Haozhuge, Tony Liu, Ying Zhang, Ajit Matthews, Afros, Mohyuddin, Vinay Rao, and Dhruv Chaudhary for providing support and useful feedback on this work. And in particular, we have the proof of the determinant version in the appendix, and we also have the entire Triton forward and backward pass in the paper. So, and there's also a GitHub repository that's trying to put this together. Yeah, so I will give some time for questions for people. Yeah, if anybody has any questions.
Yeah, thank you for your talk. I have a question. So have you ever measured the scaling or curve using like normal text data instead of this JMSF AK? and stuff like that.
Yeah. Like I said, this does not help. This does not help regular text tasks, right? So if we measure, right, so this will improve the overall loss by a little bit, but not by a lot. And where what we show is where it's improving the loss, right? Improving the loss can come from various different axes, right? So you can reduce the loss on knowledge tasks, reasoning tasks, or you could reduce the loss on NLP tasks. And all of these, like the overall loss is an average of those losses, right? So it loses more information. So if you measure the scaling law with respect to the, the overall loss, you may see a smaller alpha, right? Because it will be, right? So GSM8K has a larger alpha, MMLU has a smaller alpha, MBPP has a smaller alpha. Now, if you look at non-math coding or reasoning tasks like, I don't know, like machine translation or summarization, it will have it will have a neutral alpha, right? It will have the same alpha as a transformer because there's no reason for it to help the NLP tasks. So the overall alpha for, if you just measure over your validation set, which is going to be an average over all of these, then that will certainly be lower, right? So what I'm saying is that if you want to push these models further, it no longer suffices to just look at the average loss. We need to start breaking down losses by categories and start thinking of how to add more compute to drive down each of these losses. So this is, yeah, that's sort of the idea here.
Have you ever tried training on, for example, code corpus or mathematical corpus, for example, like proof prior?
Have I tried training what?
Training the model directly on mathematical or coding corpus, such as proof pile, so you can directly measuring the scaling law curve there.
Right. So this is trained on the same mixture as the Llama 4 or Llama 3 mixture. I think it was the Llama 3 data mix. So it has some proportion of math and code in it already. We have not tried training it on only on math and code. I guess that could be one. Yeah, that could be. So obviously, right. So if you want, yeah. This has some proportion. This has a certain proportion of math and code in it already. So this we haven't tried it training it only on math and code. So this should be something that's future exploration that people can try. So yeah.
Yeah, I see, I see. Final question. So
Mhm.
have you ever tried using some IR method to use this method for transfer?
Right, right. So RL, right. So there's two axes to RL, right? So RL, so if you believe in pre-training versus RL, right? So what does pre-training so what does RL do, right? RL, so there's like multiple papers now. Most recently is the paper by Yejin Choi, where she shows that RL amplifies already that are things that are there in the model's generation space, right? So, for example, if something is not in the model's generation space, right? If the model assigns zero probability to the correct answer, then RL is not going to be able to unlock that, right? Because the RL essentially tries to sample from the model, and then for correct answers, it tries to sort of amplify that, right? So you still need better pre-trained models that have the correct answer in your generation space, right? If you look at the pass at k, or if you look at the, you know, the k, if you sample k times the k most probable generations, then RL essentially hones in on things within that, right? So you still need better pre-trained models together with RL to unlock both of these capabilities, right? So we have inference time compute, which is RL, and you also want to spend more compute during pre-training to improve math and code, and you want to do RL with this. So this should help you unlock like a stronger class of like the more challenging problems that even with RL we can't solve, right? So that's sort of the idea. So this would have been a to-do if I stayed at Meta. I would have RL this model and whatever, but I'm not in Meta anymore, so people there can try it.
Yeah, thank you for your explanation. Yeah, I'm very interested in the result on those reasoning tasks using this method.
Right. I mean, the way to think about RL is like I have a very intuitive explanation for it. We can think of these models as like human brains, right? This is the human brain. And then RL and pre-training is where the brain is thinking about, it's reading a book and it's thinking about the book, right? It's trying to learn some knowledge about the book. And then RL is like testing, right? It's like a standardized test. Like once you read your books in your childhood, you are you go to school and you're giving text, you're giving exams, and you get feedback on the correct answer versus incorrect answer, right? So RL essentially gives you that feedback, so you become a better and better at answering the standardized test. But then what still matters is if you are a deeper thinker, or if you're like a smarter person, even with a standardized test, you you can solve, you can like a smarter brain still matters. It's not just the standardized test that can unlock everything. So this is sort of making the point that this is sort of a smarter brain because it computes a more expressive function during pre-training, right? So if you do a standardized testing, which is RL, on it, it will solve a richer class of problems, right?
Yeah, thank you. We have another question in the chat.
Mhm.
So I'll read it. So in the scaling curve, Hoffman report alpha to be around 0.3. Do you have an explanation why do you get alpha around 0.1?
Yeah, the Hoffman et al. Is for the whole train set, right? It's the validation set. My alpha is for the GSM8K MMLU. It's a pair task-wise alpha, right? Whereas if you compute the alpha over the whole training set or the validation set, not just the math tasks, you will get a different alpha, right? So the Hoffman et al. Alpha is an average of the alphas over all these categories, right? They never measure an alpha per task. They measure alphas over their validation set. So my claim is that math, coding, reasoning tasks are more challenging. So they will have the harder the task, the lower will be the alpha, right? It's harder to the more challenging the task, the harder it is to improve, right? Whereas, for example, if you have a very easy task, you can just improve it very, very quickly, so you'll have a high alpha, right? So that's the reason why the alphas are different compared to Hoffman.
Yeah, thank you for the answer. Do we have any other question?
Good question. So I'm not sure whether I understand this correct. Is that for
Mhm.
two simply
Mhm.
simply sure, I mean your design
Mhm.
it means a higher attention.
Mhm.
it's kind of like the attention of attention.
Correct.
So it means so it's Q, K, V, and K prime and V prime. So it's kind of like the attention of attention.
Right. Attention of attention. Yeah, I guess you could call it that. Yeah.
Uh,
Mhm.
Also, but for the parameter, why the like transformer and the attention of attention, they have similar parameter size. I mean,
They have similar parameter size, yes.
uh, but but how do you do that? So you use sliding windows to like because from my understanding, higher order attention, it should you might need more parameters to do that. But
No, what I said was,
mhm.
right, so you have very small number of parameters, right? So you get WK prime and WV prime,
Yes, yes,
right? So this is just a D by D matrix. So this is the additional parameter you choose, right?
yes.
So you have slightly more parameters, right? So let's look at this active parameters, right? So what we fit is we fit the active parameters to the alpha, right? We fix this, we fix away this term, and we fix this active parameters to alpha. And for both transformers, so transformer has 1b, this has slightly, so if I break down this number, it's not going to be exactly 1b, it's going to be one, 1 point something something, and this will be 1 point something something, a little bit bigger than this, right? Because it has WK prime and WV prime in addition to this, right?
Mhm.
And this will be also something in addition to, to 2 billion, right? So both of these. So for this scaling law curve, I've fit the exact number of active parameters for both of these models. So the two simplicial has slightly more active parameters. But the point is that it's doing more work per parameter, right? So you're sort of getting more bang for your buck, right? So what you can see, for example, in GSM8K is that at 1 billion, you're sort of neutral. At 2 billion, you're starting to see some gains. And at 3 billion on GSM8K and MMLU Pro, you're starting to see more gains, right? So this means that you're adding slightly more parameters, but your slope is steeper, right? So your alpha is bigger. And so you can estimate that, right? It's essentially log linear, right? So it's a line. So this transformer line is like this, two simplicial line is like this, like a steeper line, right?
Also, do you have any observation on the sparsity of the attention of attention and the attention?
On the sparsity, what do you mean by sparsity?
Maybe the rank of the attention matrix.
Oh, yeah, that's a good question. I can make the following observation. I have tried, if you look at this, um if you look at this definition, right? You can approximate this by QIL KJL plus QIL times K prime KL, right? So you can do these two attention terms. So you can do, instead of this three-way einsum, you can do a two-way einsum between Q and K, and you can do a two-way einsum between Q and K prime, and you can add that result, right? So you can do QK and QK prime and add that, and that would be a rank 1 approximation to this tensor. And what I know is that rank 1 approximation is significantly worse than this one. So it's still better than dot product attention, but it's significantly worse than this. So it certainly is not low rank, right? At least for, so you can't, so there's like Strassen attention, which does something low rank as well. And there's the rank 1 approximation that does something low rank as well. And both of them are worse than if you actually do this full two simplicial attention. So you should, yeah. So I think for some of these tasks, you want the full power of, yeah, you want the full power of two simplicial attention.
Okay, thank you.
I have another question. So,
Mhm.
in the rotary position encoding section,
Mhm.
is this position encoding double the number of flops, the total flops?
Mhm. This doesn't double. This doubles W2, right? So you increase flops by W2, attention flops by W2, right? So you have more flops, right? So, but what I'm claiming is flops are not important. What is important for generalization is number of parameters, right? So given us particular number of tokens, let's say I have 10 billion tokens, then for 10 billion tokens, I cannot train an arbitrarily large language model, right? Because I won't generalize. My model will start memorizing everything, right? So for memorization is proportional to the number of parameters, not the number of flops, right? So this increases attention flops by W2 while keeping the number of parameters small. And that's exactly. So you're paying more attention flops. So you're trading off more compute for token efficiency. So you're trading off compute efficiency for token efficiency, essentially, is the idea.
I see. Do you have any plans to do some hybrid model? Like you only use several layers to do this more expensive attention layer, and then for the rest you can still do standard softmax attention to
Yeah,
have the
our experiments are with hybrid, right? Because we use only 1 in 4. So only it's hybrid. It's where is it? Interleaved, where every fourth layer is interleaved to simplicial attention. If it is not hybrid, if it is like fully, if you do all layers to simplicial, and if you do, if you compare to a similar size window, you will get like some crazy. You will get even more gains. You will get gains like I don't know. You will get gains like this. Right? I was. Mm, uh, Here. You will get gains like this, right? So for example, yeah, this is for example, if you reduce the context length so that every layer is a 32 size is 32 context. So it's 32 by 32 attention versus 32 by 32 by 32 attention, then you will get like noticeable improvements in loss. But of course, you can't do, you're comparing 32 by 32 by 32 attention to like, let's say full attention with 512 sequence length. So your gains would be lower, but yeah. So you're spending more attention flops, right? So you are driving down the loss by spending more attention flops, right? So that's the claim. And then the idea is that for large language models, right, we can no longer keep scaling the transformer, right? Because in we don't have enough tokens, right? So if you have like people back in the day were scaling, like they were thinking if you just keep scaling transformer, you will get AGI or whatever, right? That's just not going to happen because whatever, the largest GPT 4.5, for example, was a very large model, but it's worse than the smaller models. Why? Because it has way more parameters and not enough tokens, right? So it's essentially does not generalize. That's the problem. So you want to find ways for a smaller number of parameters to generalize better. So this is sort of one way to do that, if that makes sense.
Yeah, it makes sense. Thank you. Okay, seems that we do not have further question from the audience. Thank you.
Can I ask one question?
Okay, sure.
I don't know if this has been answered before. It's like why we use like MOE for the experiment instead of like dense model?
That's a good question. That's because of Meta's Llama, whatever baselines. This were the baselines I had to work with. You can use a dense model, and the results should be similar. I was in a rush. I had to get the paper out before the super intelligence reorg or whatever. You can do the same experiments with dense models, but this was sort of the baseline at Meta. But you can. I mean, MOEs in some sense are a stronger baseline, right? So dense model you can improve it easily, but MOEs also have a lower loss because they store more information, right? They're more parameter heavy. So in some sense, MOE is a stronger baseline. I guess you could think of it that way. So if it works for MOEs, it'll surely work for dense.
Okay. How many parameters here, like for the attention parts? For I'm assuming just like a few hundred million, like of just
Yeah, a few hundred, million. Yeah, attention is like insignificant part of the flops or parameters, right?
Okay.
So most of your parameters are in the FFNs anyway.
Yeah,
Okay.
I think like speaking of mixture of expert, I think like for those like fine-grained MLE, during actual training, the most expensive one comes from the mixture of expert part. Do you think this gives an opportunity to design some more expensive and more expressive attention variant, to Simplex your attention?
What gives more? Sorry, I didn't get the question.
Give you more opportunity to use this more expensive attention variant because
Sure.
during actual training, the attention part must be waiting for the MOE
Exactly.
with
Yeah.
those communication costs. And
Correct.
one strategy is just we can increase the flops and the total amount of like time spent on the attention part. So
Correct. Exactly.
so these two parts, the attention layer
Right.
and the issue of expert layer could be better overlapped. Yeah.
Exactly. That's exactly right. Yeah. Especially you could also think of doing like some sort of parallel attention or parallel transformers or something where you're doing essentially if your FFNs are waiting on if your devices are waiting on FFNs, then you can start doing more crazy stuff on the attention, and you will, exactly.
Yeah, very interesting. Yeah.
Yeah, I mean,
Yeah, I can foresee a lot of opportunity for this more expensive attention variant in the future, because
exactly.
MLE dominates the total training time.
Either MOE or the global attention layer, right? So if you start spending more, if you're serving like 1 million queries, so if you have like the sliding window local layers, and then you have the 1 million global attention layers, and you're doing some sort of pipelining, then you can always insert this layer into the local attention layers because your global attention layers will start dominating. So this has sort of because attention is so insignificant part of the compute right now that everything's dominated by FFNs or by the global attention layers. So I think we should start putting more compute on local attention to drive down the loss even more.
Yeah, cool. Do we have other questions, or we'd better wrap it up here? Okay, it seems that we do not have further question. Thank you, Aurko.
Thank you so much. Thanks for having me.
Yeah, thank you again for giving the talk. Yeah.
Absolutely. Thank you. My pleasure. Bye.